You're drifting through a cloud so vast that light takes years to cross it, and you feel nothing. A few atoms of hydrogen wander through every cubic centimetre, thinner than any vacuum ever created on Earth. Cold, dark, and perfectly still. In 1864, William Huggins proved that these faint cosmic smudges were not distant stars. They were enormous clouds of gas. Some stretch across dozens of light years. The Orion Nebula alone holds enough raw material to build thousands of suns. Yet for millions of years, almost nothing moves. No one could explain how something so empty could ever become something so violent. Then in 1902, James Jeans calculated the exact conditions under which gravity would finally win, and the sky confirmed his numbers. What happens next is one of the slowest, most beautiful processes in the known universe, and it is unfolding right now. Tonight we drift through stellar nurseries, watch gravity gather the dust, and follow a collapsing cloud all the way to first light. If this channel helps you unwind, a like or subscribe truly helps. The nursery awaits. Step inside. The space between the stars looks empty. If you could stand in it, suspended somewhere in the gulf between our sun and its nearest neighbour, you would see nothing. No light, no warmth, no movement. Just darkness in every direction, stretching for years at the speed of light. But it is not empty. It has never been empty. Scattered across every galaxy in the observable universe, threaded through the spiral arms, pooled in the spaces between stellar neighbourhoods, drifting in vast tendrils that stretch across hundreds of light years, is a thin, cold sea of gas and dust. Astronomers call it the interstellar medium, and it is the raw material from which every star that has ever existed was built, including the one that keeps you alive. Most of it is hydrogen, the simplest element in the periodic table. One proton at its centre, one electron in orbit around it, nothing else. No complexity, no structure, no chemistry worth mentioning. Just the most basic building block the universe has to offer, drifting alone through the dark. And there is almost none of it. That is the part that defies intuition. If you could scoop up a cubic centimetre of this interstellar gas, a volume no bigger than a sugar cube, you would find, on average, roughly one atom inside it, sometimes a few more, sometimes fewer. Compare that to the air you are breathing right now, which contains approximately 25 billion molecules in the same volume, and the difference becomes staggering. The interstellar medium is not just thin, it is thinner than the best vacuum any laboratory on Earth has ever achieved, by several orders of magnitude. And yet, this almost nothing is the starting point for everything that follows. In some regions of the galaxy, the hydrogen is hot, thousands of degrees. Energized by the ultraviolet radiation pouring off nearby massive stars, these atoms lose their electrons and become ionized. Electrically charged particles glowing faintly in pinks and reds and blues. These are the regions you may have seen in photographs of deep space. The bright, sculpted clouds that decorate the arms of galaxies. Beautiful, luminous, and entirely the wrong place to build a star. Because star formation does not begin in the hot gas, it begins in the cold. Far from any star, far from any source of energy, there are regions where the hydrogen cools, where the atoms slow down, lose their kinetic energy, and drift with almost no motion at all. And in those cold, lightless places, something remarkable begins to happen. Something that was not understood for centuries, and that even today still holds surprises. For most of astronomical history, the faint smudges visible between the stars were a mystery. Some astronomers believed they were simply distant clusters, thousands of stars too far away to resolve individually, blurring into a soft glow. Others suspected they were something else entirely, though no one could say what. The answer came on an August evening in 1864, when William Huggins pointed a spectroscope at a faint nebula in the constellation Draco, a small round smudge catalogued as NGC 6543. What he saw through the eyepiece changed astronomy. Instead of the continuous rainbow of colours that a cluster of stars would produce, Huggins found a handful of bright, isolated emission lines. The signature not of countless distant suns, but of a single glowing gas. It was the first direct proof that at least some nebulae were not made of stars at all. They were enormous clouds of gas, hanging in the void between stellar systems, lit from within or without by the energy of their surroundings. Huggins went on to examine other nebulae, including the Great Nebula in Orion, and confirmed the same result. The universe contained vast reservoirs of raw gaseous material, and no one yet understood what they were for. It would take more than a century of physics, chemistry, and observation to answer that question fully. But the answer, when it came, was extraordinary. When hydrogen atoms cool enough, below roughly 100 Kelvin, which is approximately minus 170 degrees Celsius, they begin to do something they cannot do at higher temperatures. They bond. Two hydrogen atoms meet, interact, and form a single molecule, molecular hydrogen. It is a quiet event. No flash of light, no release of dramatic energy. Just two atoms finding each other in the cold and holding on. But when enough molecular hydrogen accumulates in one place, the consequences are anything but quiet. What forms is called a giant molecular cloud, and the name barely does it justice. A single giant molecular cloud can stretch across 300 light years. It can contain enough raw material to build not one star, not 100, but millions. The mass inside one of these structures can exceed 1,000,000 times the mass of our Sun. They are among the largest coherent objects in any galaxy, sprawling, irregular, threaded with filaments and knots and dense pockets that shift and churn over timescales far longer than any human civilization. And yet, for all that mass, they are phenomenally diffuse. A cubic centimetre inside a giant molecular cloud might contain a few hundred molecules. In the denser cores, perhaps a few thousand. That is better than the general interstellar medium, certainly, but it is still an almost inconceivable emptiness by earthly standards. You could pass through one of these clouds at the speed of light, and, molecule by molecule, encounter less matter than exists in a single breath of air. This is the paradox at the heart of star formation. The places where stars are born are, by any human measure, virtually empty. Inside these clouds, it is dark, genuinely, profoundly dark. The dust grains, tiny particles of silicate and carbon, each one smaller than a micrometer across, absorb and scatter incoming starlight with extraordinary efficiency. Visible light from nearby stars barely penetrates the outer layers. Deeper inside, no visible light reaches at all. The interior of a giant molecular cloud is one of the most lightless environments in the known universe. And because there is no light, there is almost no heat. Temperatures in the densest regions can fall to just 10 Kelvin. That is minus 263 degrees Celsius. Colder than the void between galaxies. Colder than the faint background glow left over from the Big Bang. These are among the coldest natural environments that exist anywhere. Not just on Earth, not just in the solar system, but in the entire observable universe. In 2001, a team led by Tom Dame at the Harvard-Smithsonian Center for Astrophysics completed the most comprehensive survey ever conducted of molecular clouds across the Milky Way. Using radio telescopes tuned to the emission frequency of carbon monoxide, a trace molecule that acts as a proxy for the far more abundant but nearly invisible molecular hydrogen, Dame and his colleagues mapped the distribution of giant molecular clouds throughout the galaxy. What they found was a vast network of cold, dense structures concentrated along the spiral arms, each one a potential stellar nursery, each one containing within it the seeds of future suns. These clouds do not advertise their presence. They are invisible in ordinary light. They betray themselves only through the faint radio emissions of their trace molecules, through the shadows they cast against brighter backgrounds, and through the infrared glow of their cold dust. To the naked eye, they are nothing, dark patches in the sky, absences where stars should be. But they are the most important structures in the galaxy, because inside them, in the cold, in the dark, in the silence, gravity is waiting. And given enough time, gravity always wins. But gravity does not act alone. Not yet. Not without a fight. Inside every giant molecular cloud, a war is being waged. Invisible, silent, and relentless. On one side stands gravity, pulling inward, trying to draw the gas together, trying to compress it into something denser, something hotter, something that might one day burn. On the other side stands everything else. The first line of defense is thermal pressure. Every molecule inside the cloud, no matter how cold, is moving. 10 Kelvin is unimaginably frigid by human standards, but it is not absolute zero. The molecules still vibrate, still drift, still collide with their neighbours, and every one of those collisions pushes back against compression. It is a feeble resistance. The thermal energy inside a molecular cloud is tiny compared to the gravitational energy trying to crush it, but it is real. And in many regions of the cloud, it is enough. The second force is far more violent. Giant molecular clouds are not calm places. Despite their stillness in photographs, their interiors are churning with turbulence, chaotic, supersonic motions that stir the gas in every direction. Supersonic means faster than the speed of sound within the cloud itself, which at 10 Kelvin is only about 200 meters per second. The internal motions inside a typical molecular cloud exceed this by factors of 10 or more. Vast currents of gas sweep through the cloud, colliding, merging, splitting apart, creating shock fronts and filaments and eddies at every scale. This turbulence is not random noise. It is a structural force. It shapes the cloud from within, carving it into the complex networks of filaments and knots that modern telescopes reveal. And crucially, it provides support. The kinetic energy of all that turbulent motion acts against gravity in much the same way that thermal pressure does, by pushing outward, resisting compression, preventing the cloud from simply falling in on itself. But turbulence is a double-edged weapon. While the large-scale motions hold the cloud up, the small-scale collisions between turbulent flows do something else entirely. Where two streams of gas meet, they compress the material between them. They create pockets of higher density, regions where the gas is suddenly thicker, suddenly heavier, suddenly more vulnerable to gravity's pull. Turbulence supports the cloud on the large scale and destroys it on the small scale. It is both shield and saboteur. There is a third player in this contest, and it is perhaps the most mysterious. Magnetic fields thread through every giant molecular cloud, invisible lines of force woven into the gas, carried along by the electrically charged particles that exist in trace amounts even in the coldest, densest regions. These fields resist compression. When gravity tries to squeeze the gas perpendicular to the field lines, the magnetic pressure pushes back. The gas can slide freely along the field lines, but it cannot easily cross them. How much this matters has been debated for decades. Some models of star formation treat magnetic fields as a dominant support mechanism. The primary reason most molecular clouds do not collapse. Others treat them as secondary, arguing that turbulence does the heavy lifting and magnetic fields are merely along for the ride. The truth, as so often in astrophysics, appears to lie somewhere in between, the relative importance shifting from cloud to cloud, from region to region, depending on local conditions. In 2007, Christopher McKee and Eve Ostraker published what would become one of the most influential reviews in the field, a comprehensive synthesis of star formation theory that placed turbulence, magnetic fields, and gravity into a single coherent framework. Their analysis made something clear that had been suspected but never stated so precisely. The balance between these forces is not static. It is dynamic. The cloud is not sitting in quiet equilibrium. It is a battlefield where energy is constantly being injected, dissipated, and redistributed. Turbulence decays. Magnetic fields diffuse. Gravity never stops. The question is never whether a cloud will collapse. The question is where and when and how much of it. The governing principle behind all of this is something called the virial theorem, a mathematical relationship that weighs the total gravitational energy of a system against its total kinetic, thermal, and magnetic energy. If gravity dominates, the system contracts. If the other energies dominate, it expands or holds steady. If they are roughly equal, the system sits in a tense, temporary balance, a balance that can be tipped by the slightest change in conditions. Most of a giant molecular cloud sits in exactly this state, balanced but only barely, supported but only temporarily, and the proof of that fragility is written in the numbers. Of all the gas contained within a typical molecular cloud, millions of solar masses of raw material, only a tiny fraction will ever become stars. Star formation efficiency, as it is called, sits at just a few percent. The vast majority of the cloud will be stirred, heated, dispersed, and recycled back into the interstellar medium without ever collapsing. The cloud is not a factory working at full capacity. It is a vast reservoir of potential, almost all of which will go unrealised. But the small fraction that does collapse, the dense pockets, the compressed filaments, the regions where gravity has found an edge, those are where everything begins. The first person to put numbers to that edge was a physicist working at the turn of the 20th century. In 1902, James Jeans published a paper in the Philosophical Transactions of the Royal Society that asked a deceptively simple question. If you have a uniform, infinite medium of gas at a given temperature and density, how large does a region need to be before its own gravity overwhelms the internal pressure holding it apart? The answer was a single length, a critical size above which collapse becomes inevitable. Below that size, thermal pressure wins, the gas puffs back out, nothing happens. Above that size, gravity wins, the gas begins to fall inward, and nothing, not pressure, not heat, not motion, can stop it. This critical size is now called the Jeans length, and from it follows a critical mass, the Jeans mass, the minimum amount of material a region must contain before self-gravity takes over. The two quantities are related by the same physics, and they depend on just two properties of the gas, its temperature and its density. The relationship is elegant and intuitive. Colder gas has less thermal pressure. Molecules move more slowly, push back less forcefully, and gravity needs less mass to overcome them. Denser gas packs more matter into a smaller volume, strengthening the gravitational pull. Both changes lower the gene's mass. Both make collapse easier. Think about what that means for the interior of a giant molecular cloud. The gas is already extraordinarily cold, 10 Kelvin in the densest cores. And while the overall density is low by any terrestrial standard, the densest knot and filaments within the cloud are hundreds or thousands of times thicker than the surrounding material. In those pockets, the gene's mass can drop to just a few times the mass of our Sun. A clump of gas, no more massive than a handful of stars, spanning less than 1/10 of a light year, can find itself on the wrong side of the threshold. And once it crosses that line, there is no going back. Jeans himself was aware that his analysis contained a flaw, one that would later become known as the Jeans swindle. His calculation assumed a perfectly uniform static background medium, which is itself gravitationally unstable. If the background should also be collapsing, the entire mathematical framework becomes inconsistent. It is a genuine logical problem, and it troubled physicists for decades. But subsequent work, more rigorous treatments using expanding backgrounds, finite cloud geometries, and numerical simulations, showed that Jeans had captured the essential physics correctly. The critical mass and length he derived remain remarkably good approximations of where collapse actually begins. The swindle was a mathematical shortcut, not a physical error. Half a century later, a different approach to the same problem arrived independently from William Bonner in London and Richard Ebert in Germany. Instead of an infinite uniform medium, they considered a finite, pressure-bounded sphere of isothermal gas. A cloud with an edge, sitting inside a warmer, more diffuse surrounding medium. What they found was a maximum stable mass for such a sphere. Below that mass, the cloud could sit happily in equilibrium, pressure-supported and content. Above it, no amount of external pressure could prevent collapse. These structures, now called Bonner-Ebert spheres, gave astronomers something they could actually look for. And when radio telescopes and infrared surveys began mapping the dense cores inside molecular clouds, they found objects that matched the predictions with remarkable precision. Small, cold, roughly spherical concentrations of molecular gas hovering near the critical mass, waiting for something to push them over the edge. The Jeans criterion is not a trigger. It does not explain why collapse starts. It explains when collapse becomes possible. It draws a line in the physics, a boundary between stability and catastrophe. And it says, beyond this point, gravity wins. Every pocket of gas inside a molecular cloud can be measured against that line. Most fall safely below it. A few sit right at the boundary, and a very few have already crossed it. What pushes them over is a different question entirely, and the answer is not always the same. A molecular cloud can sit at the edge of instability for millions of years, balanced but only barely, supported by turbulence that is slowly decaying, threaded with magnetic fields that are gradually diffusing, cooled to temperatures where the Jeans mass hovers tantalizingly close to the masses of its densest cores. Everything is in place. The raw material is there. The physics permits it. And yet nothing happens. Because in most cases, the cloud needs a push. The most dramatic push comes from dying stars. When a massive star reaches the end of its life, when its core has fused its way through hydrogen, through helium, through carbon and oxygen and silicon, all the way to iron, it collapses in on itself and detonates, a supernova. For a few weeks, it outshines the entire galaxy. And the blast wave it produces, an expanding shell of superheated gas travelling at thousands of kilometres per second, races outward into the surrounding interstellar medium, sweeping up everything in its path. When that shockwave encounters the edge of a molecular cloud, the effect is immediate and violent. The gas at the boundary is compressed. Densities spike. Temperatures shift. Regions that were sitting just below the gene's mass are suddenly pushed above it. The shockwave does not create the material for star formation. It was already there. What it does is rearrange it. It takes gas that was stable and makes it unstable. It takes a cloud that was waiting and gives it a reason to fall. But supernovae are not the only trigger. They are not even the most common. The galaxy itself provides a slower, steadier compression. The Milky Way is not a solid disk. It is a rotating structure with spiral arms, regions of higher stellar and gas density that wind through the galactic plane. As molecular clouds orbit the galactic centre, they periodically pass through these arms. The increased gravitational pull and gas pressure within a spiral arm squeezes the cloud from the outside, compressing its contents, nudging marginal regions past the threshold. It is a gentle trigger by comparison, no explosion, no shockwave, but it operates continuously across the entire galaxy, and it is responsible for a significant fraction of all star formation in disk galaxies like ours. Then there are the collisions. Giant molecular clouds are not stationary. They drift through the galaxy at velocities of tens of kilometres per second, and occasionally two of them meet. The merger is slow by human standards. It unfolds over millions of years. But the result is a vast compression event. Gas from both clouds is forced together, densities climb, and the combined structure produces a burst of star formation far greater than either cloud could have managed alone. And then there is the trigger that creates some of the most iconic images in all of astronomy. In 1995, Jeff Hester and Paul Scowen at Arizona State University pointed the Hubble Space Telescope at a small region within the Eagle Nebula, a star-forming complex roughly 7,000 light-years from Earth, catalogued as Messier 16. What the telescope captured became one of the most famous astronomical photographs ever taken. 3 towering columns of dense gas and dust, silhouetted against a glowing background of ionized hydrogen, stretching across light-years of space. The pillars of creation. What Hester and Scowen's observations revealed was a process called photoevaporation. The pillars were being sculpted, actively, visibly, by the intense ultraviolet radiation pouring off a cluster of massive young stars nearby. That radiation was eating into the surface of the cloud, stripping away the outer layers of gas atom by atom, molecule by molecule. But where the gas was denser, where knots of material resisted the erosion, the pillars held. And at the tips of those pillars, compressed by the very radiation that was destroying the cloud around them, new stars were forming. This is radiative triggering. The radiation from one generation of stars compresses the remnants of the cloud that created them, and from that compression, a new generation is born. It is star formation driven by destruction. A process that dismantles the nursery even as it seeds the next crop of stellar embryos. The truth is that no single trigger dominates. Different regions of the same molecular cloud can be pushed into collapse by entirely different mechanisms. A supernova shockwave may strike one edge, while a spiral arm passage compresses the opposite side. Radiation from nearby massive stars may sculpt pillars in one corner, while a slow, turbulent compression produces dense cores in another. The triggers overlap, combine, and interact. The result is that star formation within a single cloud is messy, staggered, and unpredictable. New collapses initiating across the structure over millions of years, each one the product of a unique combination of forces. But once the trigger has done its work, once a pocket of gas has been nudged past the gene's mass and gravity has the upper hand, what follows is remarkably consistent. The physics takes over, and the first act of stellar creation begins. It starts slowly, far more slowly than you might expect. Imagine a region roughly 1/10 of a light year across, a dense core inside a molecular cloud, a knot of cold molecular hydrogen that has just crossed the threshold. Gravity has the advantage. The core begins to contract. But this is not a dramatic implosion. Not yet. The molecules are drifting inward at less than 1 kilometre per second. The entire core is falling in on itself. Yes, but at a pace that makes glaciers look urgent. From the outside, if you could watch it in visible light, which you cannot, because the core is buried deep inside a dust cloud that admits no light at all, nothing would appear to be happening. The change, measured in human lifetimes, would be imperceptible. This first phase of collapse is called free fall, though the name is misleading. True free fall implies nothing resisting the motion, and that is not quite right. Thermal pressure is still there, still pushing back, but it is losing. The gravitational pull has overtaken it, and the gas is being drawn inward faster than pressure can restore equilibrium. The balance has broken, and it cannot be restored. The process will take roughly 100,000 years. 100,000 years of quiet, invisible contraction. Gas molecules drifting inward through the dark, slowly gathering, slowly compressing, slowly building something from almost nothing. During this first phase, something counterintuitive happens. As the gas compresses, the molecules collide more frequently. Every collision generates a tiny amount of heat. The core should, by all rights, be warming up. And it is, but only barely, because the gas is still thin enough, still transparent enough, that the heat escapes almost as fast as it is created. Infrared photons, produced by the collisions between molecules and dust grains, radiate outward through the cloud and vanish into space. The core generates heat and immediately loses it. The temperature barely changes. This is the isothermal phase. Isothermal means constant temperature. The collapsing core compresses by orders of magnitude, density climbing from a few thousand molecules per cubic centimetre to millions, to billions. And through all of it, the temperature holds nearly steady. 10 Kelvin, perhaps 15. The gas is falling, thickening, concentrating, and yet it remains almost as cold as when it started. This single fact, that the collapse proceeds nearly isothermally, has enormous consequences. Because temperature controls the gene's mass, and the gene's mass determines the smallest scale at which gravity can win. As the density rises and the temperature stays flat, the gene's mass inside the collapsing core drops. It fragments. Smaller regions within the core cross their own threshold and begin collapsing independently, each one a potential star in its own right. The isothermal phase is not just a collapse, it is a multiplication event. One collapsing core becomes several. Several become many. This is how a single dense core can produce not one star, but a small group. Siblings born from the same pocket of gas. In 1969, a young researcher named Richard Larson published a paper that would define the field for decades. Working at the California Institute of Technology, Larson constructed the first detailed numerical simulation of a collapsing protostellar cloud. Tracking the gas from its initial state as a cold, diffuse core all the way through to the formation of a dense central object. It was painstaking work. The computers of the era were primitive by modern standards, and the physics involved, hydrodynamics, radiative transfer, thermodynamics, pushed them to their limits. What Larsen's simulation revealed was a collapse that unfolded in two distinct stages. The first stage was the isothermal freefall, the quiet, steady compression that had been theorized for years. But what happened next had not been fully appreciated before. As the center of the collapsing core grew denser and denser, it eventually reached a point where it could no longer radiate its heat away. The gas became opaque. Infrared photons, instead of escaping into space, were absorbed by neighbouring molecules and re-emitted, bouncing from particle to particle, trapped inside the shrinking core. The moment the core became opaque, everything changed. Heat could no longer escape. Temperature began to rise in earnest. And with rising temperature came rising pressure. A new resistance to gravity that slowed the contraction and, for a time, halted it entirely. But the collapse was not finished. It had only paused. What Larsen had discovered was not a single collapse, but a two-stage process. A first fall followed by a pause, followed by a second, far more violent contraction. The details of that second stage, what drives it, how it unfolds, and what it produces, would transform the understanding of how a cloud becomes a star. That second fall is where the real violence begins. The centre of the collapsing core has become a trap. Gas is still falling inward from every direction, pouring in from the surrounding cloud, accelerating as it drops deeper into the gravitational well. But at the very centre, something has changed. The density has climbed so high that the gas is no longer transparent. Infrared photons, which for 100,000 years carried heat outward and kept the collapse cool, are now absorbed almost as soon as they are emitted. They bounce from molecule to molecule, from dust grain to dust grain, unable to find a way out. The core has sealed itself shut. And so the temperature begins to rise. Not gradually, not gently. The heat that was being generated all along by compression, by collisions, by the slow but relentless work of gravity converting gravitational energy into thermal energy, is now trapped inside a shrinking volume. The temperature climbs from 10 Kelvin to 50, from 50 to 100, from 100 to several hundred. The gas, which spent 100,000 years barely changing temperature at all, is now heating rapidly, and with every degree gained, the pressure inside the core climbs with it. This rising pressure fights back. It pushes outward against the infall, decelerating the collapse, and eventually, temporarily, it wins. The contraction slows, then it stops. For the first time since the collapse began, the centre of the core reaches a state of balance. Gravity pulling inward, pressure pushing outward, neither gaining ground. This is the first hydrostatic core, the first Larsen core, named for the man whose simulations first revealed it. It is a small, warm, pressure-supported object, roughly 5 astronomical units across, which is about the distance from the Sun to Jupiter. It is denser than anything that has existed in this region of space for billions of years. And it is completely invisible. Buried deep inside its dusty cocoon, it emits no light that any optical telescope could detect. It exists only in the infrared, and even there, only faintly. But it is not a star. It is not even close. The first Larsen core is a temporary structure, a pause in the collapse, not an end to it. It is stable only as long as the molecular hydrogen at its centre holds together. And molecular hydrogen has a breaking point. At approximately 2000 Kelvin, molecular hydrogen dissociates. The bond between the two atoms snaps. Each molecule splits back into two individual hydrogen atoms. This is not merely a chemical change, it is an energy catastrophe. Breaking molecular hydrogen apart requires energy, a great deal of it, and the only source of energy available is the thermal energy of the gas itself. As the temperature at the centre of the first core climbs toward 2000 Kelvin, the dissociation begins. Molecules break apart. Energy is absorbed. The temperature, which should be rising with continued compression, stalls. The gas is being compressed. Gravity is doing work on it. Heat is being generated. And all of that heat is being swallowed by the dissociation of hydrogen. It is as though the core has sprung a leak. Energy pours in, and the molecules drink it up. The effect on pressure is devastating. Temperature stops rising, pressure stops climbing. And gravity, which had been held in check by that pressure, suddenly finds itself unopposed. The second collapse begins. It is nothing like the first. The first collapse unfolded over 100,000 years. A slow, quiet gathering of cold gas in the dark. The second collapse takes years. Perhaps a decade. Perhaps less. The innermost region of the core, the part where hydrogen is actively dissociating, falls inward in a violent, runaway contraction. The density spikes by orders of magnitude. The radius shrinks from astronomical units to something closer to the size of Jupiter's orbit. It is the most rapid, most violent phase of the entire star formation process, and it is over almost before it begins. When the dissociation is complete, when all the molecular hydrogen at the centre has been torn apart into atomic hydrogen and there is no more energy being siphoned away, the temperature begins to rise again, rapidly this time. Pressure rebuilds, and for the second time, the collapse is halted by a new equilibrium. This is the second Larsen core. It is tiny, it perhaps a few times the radius of Jupiter, and it is dense, and it is hot, and it is real. Unlike the first core, which was a temporary way station, the second core is a genuine, long-lived object. It is in hydrostatic equilibrium. It is growing, fed by the gas still raining down from above. And it will persist, contract, and heat for thousands of centuries to come. It is, at last, a protostar. But that word requires care. A protostar is not a star, not yet. It produces no energy through nuclear fusion. Its core is hot, thousands of Kelvin, but nowhere near the millions of degrees required to ignite hydrogen burning. Every photon it emits, every erg of energy it radiates into the surrounding cloud, comes from a single source: gravity. The protostar glows because it is contracting, and contraction converts gravitational potential energy into heat. It is a machine powered entirely by falling. From the outside, if you could strip away the layers of dust and gas obscuring it, the protostar would be a dim, swollen, reddish object. Larger than the Sun, but cooler. Luminous in the infrared, but invisible in optical light. Its surface temperature is low by stellar standards, perhaps 2,000 or 3,000 Kelvin. But its interior is far hotter, and growing hotter by the day as infalling material adds mass and compression does its patient work. The protostar is not alone in its cocoon. Surrounding it is a thick envelope of gas and dust, the remnant of the original dense core that spawned it. Material from this envelope is still falling inward, drawn by the protostar's gravity, feeding it continuously. At this earliest stage, the envelope contains far more mass than the protostar itself. The central object is just a seed, a dense kernel at the heart of a much larger collapsing structure. most of the mass that will eventually compose the finished star has not yet arrived. This is what makes detecting newborn protostars so difficult. They are buried. The dust surrounding them is so thick that it absorbs virtually all the radiation the protostar emits at short wavelengths. Visible light cannot escape. Even near-infrared light is blocked. The only wavelengths that penetrate the envelope are far infrared and submillimeter, long, low-energy photons that pass through dust the way radio waves pass through walls. To find a protostar at its youngest, you need telescopes that see in wavelengths your eyes never could. In 1993, a team of astronomers introduced a classification system that gave structure to the messy, continuous process of early stellar evolution. Philippe André, working at the Commissariat à l'Énergie Atomique in Saclay, France, along with Derek Ward-Thompson and Mary Barsoni, identified a stage of protostellar development younger than anything that had been formally recognised before. They called it Class 0. A Class 0 protostar is the youngest, most deeply embedded type of stellar embryo. Its envelope still vastly outweighs the central object. It is detectable only at sub-millimeter wavelengths, the longest infrared light, just short of radio waves. It drives powerful outflows, though the mechanism behind those jets was still being debated, and it is accreting mass at a furious rate, growing heavier with every passing century. The object that cemented the classification was a source buried deep inside the Rho Ophiuchi cloud complex, one of the nearest star-forming regions to Earth, roughly 400 light-years away. Designated VLA 1623, it was invisible at every wavelength shorter than the far infrared. It was cold, dense, deeply shrouded, and unmistakably young. It became the prototype for the entire Class 0 category, proof that the very earliest stages of stellar life could be observed if you knew where and how to look. As a protostar ages, as more of the envelope rains down onto the central object and the surrounding cocoon thins, it transitions from Class 0 to Class 1. The boundary is not sharp. It is a gradual shift in the balance of mass between envelope and protostar. In the Class 0 phase, the envelope dominates. In the Class 1 phase, the protostar begins to outweigh its surroundings. More of the original core has been consumed. The cocoon is thinning. The protostar is growing. And for the first time, shorter wavelength infrared light begins to leak through the dust. Faint, but detectable. This transition unfolds over roughly 100,000 to a few 100,000 years. A blink, in cosmic terms. But within that blink, the central object has grown from a tiny seed, a fraction of the final stellar mass, into something substantial. Something with a disk of orbiting material. Something with jets of gas streaming from its poles. Something with a future. It is still not a star. The core temperature is climbing 10,000 Kelvin, 50,000, 100,000, but the threshold for nuclear fusion remains far above. The protostar has a long way still to fall before it can sustain itself, but the scaffolding is in place. The mass is accumulating, the heat is building, and the clock is running. What happens next will take millions of years, and it begins with something spinning. The original cloud was rotating, only slightly, so slightly that no instrument could have measured it from the outside. A faint, residual spin inherited from the turbulent motions of the giant molecular cloud, a whisper of angular momentum carried inward by the gas as it fell. For most of the collapse, this rotation was irrelevant. The core was so large, so diffuse, that the spin was spread across a vast volume and its effects were negligible. But angular momentum obeys a law that cannot be broken. As the core contracted, the rotation sped up. Not because any new force was applied, but because the same momentum was being concentrated into a smaller and smaller space. It is the same principle that makes a figure skater spin faster when they pull their arms inward. The total angular momentum stays the same, but the shrinking radius demands a higher velocity. The collapsing core had been turning imperceptibly for 100,000 years. Now, as it compressed to a fraction of its former size, that imperceptible rotation became something real. And it created a problem. Gas falling directly toward the protostar from above or below, from the poles of the rotating system, has no angular momentum perpendicular to the axis of spin. It falls straight in, unimpeded, and crashes onto the surface of the growing object. But gas approaching from the sides, from the equatorial plane, carries angular momentum. It cannot fall straight in. Conservation of angular momentum forbids it. The closer it gets, the faster it must orbit, and at some point the orbital velocity is high enough that the gas enters a stable orbit rather than continuing to fall. The result is a disk. Material spiralling inward from the equatorial plane of the collapsing envelope settles into a flattened, rotating structure surrounding the protostar. An accretion disk. It is one of the most important objects in all of astrophysics, a feature that appears not only around newborn stars, but around white dwarfs, neutron stars, and supermassive black holes. Wherever matter falls towards a central object, with even a trace of angular momentum, a disk forms. The physics demands it. Around a young protostar, the accretion disk is a turbulent luminous structure. Its inner edge skirts close to the protostellar surface, orbiting at tremendous speed, kilometers per second. Its outer edge extends outward for hundreds of astronomical units, far beyond the orbit that Neptune traces around our Sun. Between those extremes, the gas spirals slowly inward, losing angular momentum through friction and turbulence, radiating heat as it goes. The disk glows. Not in visible light, it is still too deeply embedded in dust for that, but in the infrared, it is bright. The heat generated by friction within the disk can rival the luminosity of the protostar itself. The internal structure is not uniform. The disk rotates differentially, faster at the inner edge, slower at the outer rim, with every annulus in between moving at its own velocity. This shearing motion generates friction between adjacent layers of gas, and that friction is the engine that drives accretion. It transfers angular momentum outwards, allowing gas to spiral inwards and eventually fall onto the protostar. Without this friction, the disk would simply orbit forever, and the protostar would stop growing. But the accretion disk is not only a feeding mechanism, it is a construction site. The same disk that channels gas onto the protostar will in time become the birthplace of planets. Dust grains within the disk collide and stick together, growing from microscopic particles into pebbles, boulders, and eventually the cores of worlds. This process begins early. Perhaps while the protostar is still accreting, while the envelope is still falling, while the system is still assembling itself from the remnants of the original cloud. Planet formation is not something that happens after star formation is complete. The two processes overlap, intertwined from the very beginning. The evidence for this has grown dramatically in recent years. Observations from the James Webb Space Telescope have revealed protoplanetary disks in extraordinary detail, not just around mature young stars, but around objects still deeply embedded in their natal clouds. In the Orion Nebula, the telescope captured images of disks seen edge-on, dark silhouettes against the glowing background gas, their structures visible with a clarity that earlier instruments could never achieve. One of the largest designated disk, 114-426, extends across hundreds of astronomical units, a vast reservoir of material orbiting a star that has not yet finished forming. It is a snapshot of the future, a planetary system in the process of being born, captured in the act. The rate at which material moves through the disk and onto the protostar varies, but for low-mass protostars, objects that will eventually become stars like the Sun, a typical accretion rate is roughly 1/1,000,000th of a solar mass per year. That sounds vanishingly small. But sustained over 100,000 years, it adds up to 1/10 of a solar mass. Over 1,000,000 years, it builds a star. Grain by grain, orbit by orbit, the disk feeds the object at its centre, and the protostar grows. Not everything in the disk falls inward though. Not everything is consumed. Because the protostar has a secret, one that was not discovered until astronomers began looking at star-forming regions with instruments sensitive enough to see through the dust. Protostars do not just swallow material, they also throw it away. From the poles of the youngest stellar embryos, perpendicular to the accretion disk, aimed outward along the axis of rotation, narrow, fast-moving beams of gas stream into space. These are protostellar jets, and they are among the most visually dramatic phenomena in the entire process of star formation. The velocities are extraordinary, hundreds of kilometers per second. Gas accelerated to speeds that dwarf anything the original molecular cloud ever experienced, launched outward from a region close to the protostellar surface, probably from the inner edge of the accretion disk, though the precise launch mechanism remains an area of active research. Magnetic fields are almost certainly involved. The leading models describe gas being flung outward along rotating magnetic field lines that thread the disk, a process that simultaneously removes angular momentum from the infalling material and channels energy into the jet. The jets do not travel quietly. They punch through the surrounding envelope, the remnant of the collapsing core, carving out bipolar cavities that extend for light years on either side of the protostar. Where the fast-moving jet material slams into the slower ambient gas, the collision produces shock waves. The gas is heated, compressed and excited. It glows. These glowing knots of shocked gas were first catalogued in the middle of the 20th century by two astronomers working independently, George Herbig in the United States and Guillermo Haro in Mexico. Both noticed small, bright nebula patches in star-forming regions that did not behave like ordinary nebulae. They varied in brightness. They moved. They appeared in pairs, straddling dark clouds where something unseen was clearly hiding. These objects are now called Herbig-Haro objects, and they remain among the clearest signposts of active star formation. When you see one in an image of a nebula, a bright, bow-shaped knot of glowing gas, you are looking at the visible consequence of a protostellar jet ramming into the interstellar medium at hundreds of kilometers per second. The jets are not continuous streams. They are episodic, bursts of material launched at intervals, each burst producing its own shock front, its own glowing knot. A single protostellar jet can display a chain of Herbig-Haro objects strung out across light years of space, each one a frozen record of a past eruption, each one moving steadily outward from the hidden source at the centre. But the jets are not merely spectacular. They serve a function, one that is critical to the outcome of the entire star formation process. A protostar accreting from a disk faces a fundamental problem. Angular momentum keeps arriving. Every parcel of gas that spirals inward carries angular momentum with it, and if that momentum simply accumulated in the central object, the protostar would spin faster and faster until it tore itself apart. Something must carry that angular momentum away. The jets are part of the answer. By flinging material outward at high velocity, the jet system bleeds angular momentum from the inner disk, allowing accretion to continue without spinning the protostar to destruction. And the outflows do something else, something final. As the jets carve their cavities, they clear the envelope. They help to remove the gas that surrounds the protostar, accelerating the transition from a deeply embedded Class 0 object to a more exposed Class 1 protostar, and eventually to a fully revealed young star. The outflows do not just sculpt the surroundings, they help end the process of infall. They set a clock on how much material the protostar can accumulate, and by clearing the envelope, they play a role in determining the final mass of the star. The accretion disk builds, the jets destroy, and between these two processes, one feeding, one stripping, the protostar finds its mass, its spin, and its future. What follows is not dramatic, it is not violent, it is not fast, but it may be the most important phase of the entire journey. The long, slow transformation of a hot, swollen, collapsing ball of gas into something that can sustain itself forever. The protostar has emerged from its cocoon. Its envelope is thinning. Its jets are carving cavities through the remnant cloud. Material is still falling inwards through the accretion disk, though the rate is slowing as the reservoir of available gas shrinks. The central object is now the dominant mass in the system, heavier than the disk, heavier than the envelope, heavier than everything around it combined. And it is contracting, not collapsing, not in free fall, not in the violent runaway manner of the second Larsen core. This is a different kind of contraction, slow, controlled, and governed by how quickly the object can radiate energy from its surface. The protostar is in hydrostatic equilibrium. Gravity pulls inward, pressure pushes outward. The two are balanced, but the star is radiating heat into space, and that lost energy means the pressure drops by a tiny fraction, and the star contracts by a tiny amount to compensate, which heats the interior by a tiny amount, which restores the pressure. It is a feedback loop, an exquisitely slow spiral of contraction, heating and radiation that will continue for anywhere from 100,000 to tens of millions of years, depending on how massive the object is. During all of this, the interior of the protostar is churning. In 1961, a physicist at Kyoto University named Toshiro Hayashi published a pair of papers that fundamentally changed how astronomers understood the early lives of stars. Hayashi demonstrated that young, low-mass stars are fully convective, meaning their entire interior, from the core to the surface, is in constant motion. Hot gas rises from the deep interior toward the surface. Cooler gas sinks back down. The star is behaving like a pot of water on a stove, boiling from top to bottom, with no layer sitting still. The reason for this total convection lies in a peculiar detail of atomic physics. In the cool outer layers of a young protostar, where temperatures sit at just a few thousand Kelvin, hydrogen atoms occasionally capture a second electron, forming what is called the hydrogen minus ion. This ion is extraordinarily good at absorbing photons. So good, in fact, that it renders the outer layers of the star nearly opaque. Light generated in the interior cannot pass through. It is absorbed, re-emitted, absorbed again, trapped in a thicket of hydrogen minus ions that refuses to let it escape efficiently. When radiation cannot carry energy outwards, convection takes over. The gas itself begins to move, physically carrying heat from the interior to the surface, the way boiling water carries heat from the bottom of a pot to the top. The entire star becomes a convective engine. Energy transported not by light, but by the bulk motion of the gas itself. Hayashi showed that this fully convective state has a profound consequence for how the star appears on the Hertzsprung-Russell diagram, the fundamental map of stellar astronomy, which plot every star according to its luminosity and its surface temperature. A fully convective protostar follows a distinctive path as it contracts. Its surface temperature barely changes, locked at a few thousand Kelvin by the physics of convection, while its luminosity drops dramatically as the radius shrinks. On the diagram, this produces a nearly vertical track. The star descends steeply, growing dimmer and dimmer at an almost constant temperature. This path is now called the Hayashi track, and it is one of the defining features of pre-main sequence stellar evolution. Hayashi went further. He demonstrated that there is a boundary on the Hertzsprung-Russell diagram, a line running roughly vertically at low surface temperatures, to the right of which no star in hydrostatic equilibrium can exist. Any object cooler than this boundary at a given luminosity would require an impossibility. It would need to transport more energy than convection can carry. The region to the right of the Hayashi track is forbidden territory. No stable star can live there. It is an exclusion zone written into the physics of stellar structure, and it constrains the appearance of every young star in the universe. The Hayashi track is not the whole story. For stars above roughly 0.7 solar masses, the convective interior does not persist forever. As the core temperature climbs, a point is reached where radiation begins to carry energy more efficiently than convection in the central regions. A radiative core develops, a zone where photons, rather than bulk gas motion, do the work of transporting heat outward. The convective envelope remains, but the star is no longer fully convective. It has developed internal structure. When this transition occurs, the star's path on the Hertzsprung-Russell diagram changes. It leaves the Hayashi track and begins moving leftward toward higher surface temperatures at a nearly constant luminosity. This horizontal phase is called the Hénier track, named for Louis Hénier, who worked out the physics of radiative contraction in the years following Hayashi's breakthrough. The star is now contracting more slowly, heating its surface and preparing for the final approach to the main sequence. The timescale for all of this depends almost entirely on one thing: mass. A protostar that will eventually become a star 10 times the mass of the Sun races through its pre-main sequence contraction in less than 100,000 years. The physics is identical: contraction, heating, convection, radiation, but the higher mass means stronger gravity, faster contraction, and a shorter journey. A protostar destined to become a star like the Sun takes roughly 10 million years. A red dwarf, a star with perhaps a tenth of the Sun's mass, may linger on the Hayashi track for 100 million years or more, contracting so slowly that entire geological epochs pass on Earth between its formation and the moment it finally ignites. For stars like the Sun, sitting somewhere in the middle of this range, the pre-main sequence phase occupies an awkward adolescence. Too hot to ignore, too cool to sustain itself, neither fully formed nor entirely embryonic. And it is during this phase that the young star first becomes visible. The envelope has been thinning for tens of thousands of years. Radiation from the protostar, combined with the relentless action of the bipolar jets, has been stripping away the surrounding dust and gas layer by layer. The accretion disk remains, a flattened structure of gas and dust still orbiting the young star, but the thick, obscuring cocoon that once hid the protostar entirely is fading. Infrared light leaks out, then near-infrared, and eventually, for the first time in the object's existence, visible light. The young star emerges. It does not emerge quietly. These objects are volatile, unpredictable, and temperamental in ways that mature stars are not. Their brightness fluctuates, sometimes by a full magnitude or more. On timescales of days or weeks, they flare, they dim, they erupt. They are still surrounded by remnant accretion disks that interact with their magnetic fields in complex, chaotic ways, channeling streams of gas onto the stellar surface along magnetic field lines and producing hotspots that rotate in and out of view as the star spins. In 1945, an astronomer at the Mount Wilson Observatory in California named Alfred Joy published the first systematic study of a group of stars that shared these peculiar properties. They were irregular variables, stars whose brightness changed in ways that did not match any known category of variability. They were found exclusively in or near dark nebulae, the dense molecular clouds where stars are born. They were faint, reddish, and surrounded by wispy nebulosity. Joy recognized them as a distinct class and named them after their prototype, a small, flickering star in the constellation Taurus. T Tauri stars. Joy could not have known the full significance of what he had found. The concept of pre-main sequence evolution barely existed in 1945. Hayashi's work was still 16 years away, but Joy had identified, for the first time, a population of stars that were not yet finished forming. Stars that were still contracting, still accreting, still settling into the configurations they would hold for billions of years. They were the visible face of a process that had begun millions of years earlier, deep inside a lightless cloud, with nothing more than a few cold molecules drifting inward under gravity's patient pull. The T Tauri phase, as it is now understood, spans the period after the envelope has largely cleared, but before the star has reached the main sequence. The young star is visible. It has a disk. It may still be accreting, though at rates far lower than during the embedded protostellar phase. Its surface is turbulent and magnetically active. It is rotating faster than it will at any later point in its life. Not all T Tauri stars are identical. The classification divides into two broad types. Classical T Tauri stars are those still actively accreting from a surrounding disk. They show strong emission lines in their spectra, signatures of gas being heated as it crashes onto the stellar surface. Their brightness variations are wild, driven by the interplay of disk, magnetic field, and infall. Weak-line T Tauri stars, by contrast, have largely exhausted or dispersed their disks. They still show the magnetic activity and rapid rotation characteristic of youth, but the accretion signatures are gone. The disk has been consumed, blown away, or has begun the process of coalescing into solid bodies, the first stages of planetary formation already underway. Both types share one critical feature. Neither is a true star, not yet. The core temperature is climbing, hundreds of thousands of Kelvin, perhaps approaching 1 million, but it has not yet reached the threshold where sustained hydrogen fusion can begin. The energy the star radiates still comes from gravitational contraction. Every photon that leaves its surface represents a tiny loss of energy, a tiny contraction of the interior, a tiny step closer to the moment when the core will finally grow hot enough and dense enough to ignite. The T Tauri star does not know it is almost there. It simply contracts and heats and waits. and the universe, which has been patient from the very beginning, waits with it. The waiting is not entirely passive. Long before the core reaches the temperatures required to fuse ordinary hydrogen, a quieter reaction begins, one that most accounts of star formation mention only in passing, if they mention it at all, but it matters. It is the first time in this object's existence that energy is produced by nuclear processes rather than by the brute force of gravitational contraction. And it changes the trajectory of the young star in ways that are subtle but real. The fuel is deuterium, a heavy isotope of hydrogen, not the ordinary hydrogen that makes up the vast bulk of the protostar, but a rarer variant whose nucleus contains not just a single proton, but a proton and a neutron bound together. Deuterium was forged in the first few minutes after the Big Bang, during the brief window when the entire universe was hot enough and dense enough to sustain nuclear fusion. It has existed ever since, mixed into the primordial gas in trace amounts, roughly 1 deuterium atom for every 50,000 ordinary hydrogen atoms. A vanishingly small fraction. But it is there, scattered through the protostellar interior, waiting for conditions that will arrive long before ordinary hydrogen can ignite. The reason deuterium burns first is simple. Its nuclear binding energy is lower. The barrier that must be overcome to fuse deuterium with a proton is smaller than the barrier for fusing 2 protons together. This means the reaction can proceed at lower temperatures, roughly 1 million Kelvin compared to the 10 million required for the proton-proton chain. And by the time the contracting protostar has been descending the Hayashi track for a few 100,000 years, the core temperature has climbed into exactly that range. The reaction itself is straightforward. A deuterium nucleus, 1 proton, 1 neutron, fuses with a proton to produce helium-3, a light isotope of helium, along with a burst of energy in the form of a gamma-ray photon. It is a clean, efficient reaction. And when it begins, it injects energy directly into the core of the protostar for the first time. But the effect is modest. There is simply not enough deuterium to sustain the reaction for long. At 1 part in 50,000, the deuterium reservoir is tiny compared to the mass of the protostar. It burns through its fuel in a cosmically brief period, a few million years at most, often far less. During that time, the energy it produces partially offsets the energy being lost from the surface, slowing the contraction. The protostar pauses just slightly. Its descent along the Hayashi track hesitates. The core temperature stabilizes for a time, held in a delicate balance between the energy being generated by deuterium fusion and the energy being radiated away. Then the deuterium runs out, and the pause ends. Stephen Staller and Francesco Palla, in their comprehensive treatment of early stellar evolution, describe deuterium burning as a brief but structurally significant event, one that shapes the early pre-main sequence track in ways that are often underappreciated. The energy injected during this phase alters the thermal profile of the core, changes the rate of contraction, and leaves an imprint on the star's position on the Hertzsprung-Russell diagram. It is not a headline event. It does not transform the object or mark a dramatic turning point. But it is the first nuclear fire. The first time that the physics of the atomic nucleus, rather than the physics of gravity, has contributed to the energy budget of this forming star. And then it is over. The trace deuterium has been consumed. The core resumes its contraction. The temperature begins to climb again, past 1 million Kelvin, past 2 million, past 5 million, rising steadily as the protostar shrinks and gravity does its patient, relentless work. The object is now approaching a threshold that everything before it has been building toward. A threshold that will change everything. The core temperature crosses 10 million Kelvin. At this temperature, ordinary hydrogen, the most abundant element in the protostar by an overwhelming margin, can finally fuse. Not deuterium, not a trace isotope, the main fuel supply. The reaction that will power the star for the rest of its life. The process is called the proton-proton chain, and it unfolds in stages. 2 protons collide with enough energy to overcome the electromagnetic repulsion between their positive charges and fuse together. One of the protons immediately converts into a neutron through a process called beta plus decay, releasing a positron and a neutrino. The result is a deuterium nucleus, the same species that burned earlier as a trace fuel now being manufactured continuously in the core. That deuterium then fuses with another proton to form helium-3. And finally, 2 helium-3 nuclei collide and merge to produce a single helium-4 nucleus. 2 protons, 2 neutrons, ejecting 2 spare protons in the process. The net result is this: 4 hydrogen nuclei go in, 1 helium nucleus comes out. Along the way, energy is released, carried away by photons, neutrinos, and the kinetic energy of the products. The amount of energy per reaction is tiny, but the number of reactions happening simultaneously in the core is beyond comprehension. Trillions upon trillions upon trillions, every second, in a volume no larger than the inner few percent of the star's radius. The numbers, when applied to a star like the Sun, are staggering. Every second, roughly 620 million metric tons of hydrogen are converted into approximately 616 million metric tons of helium. The difference, 4 million metric tons, does not vanish. It is converted into energy. Pure energy released according to the most famous equation in all of physics. Mass and energy are equivalent. They are 2 expressions of the same thing, related by the speed of light squared. 4 million metric tons of mass, converted into energy every single second, is what powers the Sun. It is what has powered the Sun for 4.5 billion years, and it is what will continue to power it for roughly another 5 billion more. The person who first understood that the energy of stars could come from the conversion of mass into energy was working in the early decades of the 20th century, long before the nuclear physics was fully understood. Arthur Eddington, one of the most brilliant astrophysicists of his generation, argued in the 1920s that the temperatures and pressures inside stellar cores were sufficient to drive nuclear reactions, though the specific reactions had not yet been identified. Eddington faced considerable skepticism. The physics of nuclear fusion was in its infancy. The quantum mechanical framework needed to explain how protons could overcome their mutual repulsion, a phenomenon called quantum tunneling, had not yet been developed. But Eddington was insistent. The energy had to come from somewhere, and chemistry could not account for it. Only the nucleus was powerful enough. He was right, and the proof came a decade later. In 1938, a young physicist at Cornell University named Hans Bethe worked out the specific nuclear reaction chains that power stars. His analysis identified 2 primary pathways: the proton-proton chain, which dominates in lower mass stars like the Sun, and the carbon-nitrogen-oxygen cycle, which dominates in more massive stars where core temperatures are higher. For this work, Bethe would eventually receive the Nobel Prize in Physics, but the immediate impact was more fundamental than any award. For the first time, humanity understood what made the stars shine. The answer was not fire, it was not gravitational contraction, though that had carried the star to this point. It was the conversion of mass into energy through nuclear fusion. a process that releases, per kilogram of fuel, roughly 10 million times more energy than any chemical reaction. The moment fusion ignites in the core of the protostar, the game changes completely. For the first time, the object has an internal energy source that does not depend on contraction. For the first time, it can radiate energy from its surface without shrinking to compensate. Gravity pulls inward. The energy produced by fusion generates pressure that pushes outward, and for the first time in the object's existence, after millions of years of contraction, after a journey that began with a few cold molecules in a dark cloud, the two forces reach a true, self-sustaining equilibrium. The star stops contracting. It has reached the main sequence. In the language of stellar astrophysics, this moment is called the zero-age main sequence, the instant at which the star first achieves stable hydrogen fusion and takes its place on the main sequence band of the Hertzsprung-Russell diagram. It is not a dramatic event. There is no flash, no explosion, no visible change from the outside. The star was already glowing. It was already luminous. But the source of that luminosity has fundamentally shifted, from gravity to fusion, from a finite process to one that can sustain itself for billions of years. And the numbers justify the word billions. A star like the Sun contains enough hydrogen fuel to sustain the proton-proton chain for approximately 10 billion years. Smaller stars, which burn their fuel more slowly, can last far longer. Red dwarfs with a tenth of the Sun's mass may remain on the main sequence for trillions of years, far longer than the current age of the universe. Larger stars burn hotter and brighter and exhaust their fuel in mere millions of years. But the principle is the same for all of them. The main sequence is the long, stable middle age of a star's life, the era when hydrogen burns steadily in the core and the star holds its shape against gravity's constant pull. Think about what has happened. A cloud of gas so diffuse that it contained fewer molecules per cubic centimetre than the best vacuum on Earth. A cloud so cold that it sat just 10 degrees above absolute zero. A cloud so dark that no visible light penetrated its interior has become a self-sustaining nuclear furnace. An object that converts millions of tons of matter into pure energy every second. An object that will shine steadily and reliably for longer than most geological features on any planet will endure. The transformation spans more than 20 orders of magnitude in density, more than 6 orders of magnitude in temperature. It covers spatial scales from hundreds of light years down to 1 million kilometres, and it takes, from the first gravitational stirring to the ignition of hydrogen fusion, somewhere between 100,000 and tens of millions of years. Gravity did this. Gravity and nothing else. No engine, no designer, no external energy source, just the weakest force in the universe, given enough material and enough time, pulling a few atoms together in the dark until they burned. But this story has been told as though it happens to one star, alone, in isolation, as though a single dense core collapses in the dark and produces a single glowing object, and that is the end of it. That is not how it works. That is almost never how it works. When a giant molecular cloud begins to fragment, when turbulence and gravity conspire to create pockets of gas dense enough to cross the gene's threshold, the process does not produce one core. It produces dozens, hundreds, sometimes thousands. Scattered across the cloud, separated by fractions of a light year, each one collapsing on its own timescale, each one building its own protostar, each one following the same physics through through the same stages toward the same destination. Star formation is not a solitary event, it is a collective one. Stars are born in groups from the same parent cloud at roughly the same time. This is not a minor detail, it is the dominant mode of star formation in the galaxy. In 2003, Charles Larder and Elizabeth Larder published a study that brought this point into sharp focus. Drawing on decades of infrared and submillimeter observations of star-forming regions across the Milky Way, they demonstrated that the vast majority of stars, perhaps 70 to 90%, are born inside embedded clusters. Not in isolation, not in pairs, in clusters. Groups of young stars, still surrounded by the remnant gas and dust of the cloud that produced them, packed into regions a few light years across, sharing the same natal material and the same gravitational environment. The implications are significant. Every star in such a cluster is exposed to the radiation, the winds, and the gravitational influence of its neighbours. Massive stars, the rare, bright, hot ones that burn through their fuel in millions rather than billions of years, pour ultraviolet radiation into the surrounding gas, heating it, ionising it, and sculpting the very cloud that is still producing new stars nearby. The environment inside an embedded cluster is not gentle. It is competitive, chaotic, and consequential. Nowhere is this more visible than in the Orion Nebula. Roughly 1,340 light-years from Earth, the Orion Nebula is the nearest large-scale star-forming region, a place where hundreds of young stars in every stage of development are visible within a single field of view. At its heart sits the trapezium cluster, a tight group of 4 massive young stars whose combined ultraviolet output illuminates the entire nebula, carving a vast cavity in the surrounding molecular cloud and flooding it with energy. Around the trapezium, in every direction, smaller and fainter stars dot the landscape. T Tauri stars still surrounded by disks, protostars still embedded in dusty envelopes, and fully formed main sequence arrivals that have already begun their long, stable lives. It is a living cross-section of the star formation process. Every stage described in this story, from collapsing cores to accreting protostars, to disk-bearing T Tauri stars, to freshly ignited main sequence objects, is represented here simultaneously within a region just a few light-years across. The Orion Nebula is not a snapshot of a single moment. It is a staggered assembly line, with new stars entering at one end and finished stars emerging at the other, the process repeating continuously over millions of years. But the environment is not benign. The massive stars at the centre do not merely illuminate the nebula, they reshape it. Ultraviolet radiation from the trapezium stars strikes the surfaces of nearby protoplanetary disks, the delicate gas-rich structures orbiting younger, lower-mass stars in the same cluster. That radiation heats the outer layers of the disks, stripping gas away molecule by molecule in a process called external photoevaporation. The disks are being destroyed, not by anything happening within them, but by the violence of their neighbours. Observations led by Olivier Bernet, using the James Webb Space Telescope, have captured this process in unprecedented detail. In a study of a disk designated 203-506, a protoplanetary disk orbiting a low-mass star in the outer regions of the Orion Nebula, Bernet and his team found clear evidence that the disk's outer layers were being stripped away by the ultraviolet field of the nearby massive stars. The disk was losing mass, its lifetime was being shortened. The planetary system that might have formed within it was being altered, perhaps irreversibly, by the environment into which it had been born. This is the paradox of cluster formation. The same process that brings stars into existence, the collective collapse of a giant molecular cloud, also places those stars in an environment that can damage or destroy the very disks from which their planets would form. Proximity is both a birthright and a hazard. Stars born near massive neighbours inherit a harsher environment than those born on the cluster's outskirts, and that difference may determine not just whether planets form, but what kind of planets they become. The diversity within a single nursery is remarkable. Stars spanning a factor of 100 in mass, from tiny red dwarfs with 1/10 the mass of the Sun, to blazing blue giants with 50 times its mass, form from the same cloud at the same time in the same region of space. Their futures could not be more different. The red dwarf will burn for trillions of years, outlasting the current age of the universe many times over. The massive star will exhaust its fuel in a few million years and detonate as a supernova, perhaps triggering the next generation of star formation in a neighbouring cloud, completing the cycle. But they will not stay together. The embedded cluster is bound together initially by the gravity of the remaining molecular gas, the material that has not yet been consumed by star formation. That gas provides a gravitational well, a shared potential that holds the young stars in rough proximity. But it does not last. Feedback from the most massive stars in the cluster destroys the gas. Ultraviolet radiation ionizes it. Powerful stellar winds push it outward. And eventually, within a few million years of the first massive stars igniting, the remaining molecular material is expelled from the cluster entirely, blown away, dispersed back into the interstellar medium from which it came. When the gas leaves, it takes most of the cluster's gravitational binding energy with it. The stars, which were held together by the combined gravity of gas and stars, suddenly find themselves in a much shallower potential well. For most clusters, this is fatal. The stars are moving too fast for the reduced gravity to hold them. The cluster expands, it loosens. Over tens of millions of years, the stars drift apart. First slowly, then more quickly, as gravitational interactions with the galaxy's tidal field and with passing molecular clouds accelerate the dispersal. Within 100 million years, the cluster is gone. Its members are scattered across the galactic disk, each one following its own orbit around the centre of the Milky Way, separated by tens or hundreds of light years from the siblings it was born alongside. They share a common chemistry, the elemental fingerprint of the cloud that made them. They share a common age, but they no longer share a common address. Our Sun was born in such a cluster. Roughly 4.5 billion years ago, in a molecular cloud that no longer exists, our star formed alongside dozens or perhaps hundreds of siblings, fellow products of the same collapsing gas, the same turbulent fragmentation, the same patient work of gravity. Those siblings are still out there, somewhere in the Milky Way, but they have been drifting apart for longer than complex life has existed on Earth. Finding them, matching their chemical signatures to the Sun's, tracing their orbits backwards through billions of years of galactic rotation, remains one of the great open challenges of stellar archaeology. The process does not end when the cluster disperses. It does not end at all, right now, at this moment, in molecular clouds scattered across every spiral arm of the Milky Way. And in the spiral arms of every other galaxy in the observable universe, the same sequence is unfolding. Clouds are cooling, cores are condensing, protostars are collapsing, disks are forming, jets are firing, and somewhere, in some dark, cold, lightless corner, of a nebula that no human eye will ever see. A few atoms of hydrogen are drifting together under the faintest pull of gravity, beginning a journey that will end millions of years from now in nuclear fire. It is the most common act of creation in the universe, and it never stops. Consider for a moment what has actually happened. A cloud of gas, hundreds of light years across, containing enough raw material to build millions of stars, has produced a single self-sustaining point of light. The journey from the first gravitational stirring in a cold molecular cloud to the moment hydrogen fusion ignites in a stellar core spans anywhere from 100,000 years for the most massive stars to tens of millions of years for the smallest. In human terms, these numbers sound enormous. In cosmic terms, they are brief. The universe has been making stars for more than 13 billion years. The process that built our sun occupied less than 1/10 of 1% of the time that has passed since. But time is only one dimension of the transformation. The spatial scales are equally staggering. The giant molecular cloud where the story begins stretches across hundreds of light years. A beam of light, the fastest thing in the universe, would take centuries to cross it. Within that cloud, the dense core that initiates the collapse is a fraction of a light year across. Perhaps 1/10, perhaps less. It is a tiny region within a vast structure, a single pocket of slightly higher density in an ocean of cold gas. And from that pocket, after the collapse, after the accretion, after the long contraction of the Hayashi track, the finished product is a star, 1,000,000 kilometers in diameter. Perhaps a little more, perhaps a little less. 1,000,000 kilometers is vast by human standards. You could line up more than 100 Earths across the sun's face. But compared to the cloud that produced it, the star is a speck, a mote, a point of light occupying an almost unmeasurably small fraction of the volume that gave it birth. The density transformation is the most extreme of all. Inside the giant molecular cloud, the densest regions contain perhaps a few hundred molecules per cubic centimetre, a few thousand in the cores. That is the starting material, a near vacuum by any earthly standard, thinner than anything achievable in the most advanced laboratories on Earth. The finished star, by contrast, has an average density of roughly 1.5 grams per cubic centimetre, comparable to water. At its core, the density reaches 150 grams per cubic centimetre, 15 times the density of lead. The transformation from cloud to star spans more than 20 orders of magnitude in density. 20 powers of 10. That is a factor of 1 followed by 20 zeros. A number so large that writing it out would fill a line, and comprehending it is effectively impossible. Temperature follows a similar arc. The coldest cores inside molecular clouds sit at 10 Kelvin, 10 degrees above absolute zero. At that temperature, molecular motion has almost ceased. The gas is as close to stillness as nature permits outside a laboratory. The core of a finished star burns at 10 million Kelvin or more, 6 orders of magnitude, a millionfold increase. From a temperature where molecules barely vibrate to a temperature where atomic nuclei are stripped bare and driven together with enough force to overcome the most powerful repulsive force in physics. Every one of these numbers is real. Every one is measured, verified, and grounded in decades of observation and theory. And every one of them describes a transformation that begins with almost nothing, a few atoms drifting in the dark, and ends with a nuclear furnace that will shine for billions of years. You carry the evidence of this process inside you. Every atom in your body heavier than hydrogen, the calcium in your bones, the iron in your blood, the oxygen in every breath, was forged inside a star that went through exactly this journey. A cloud collapsed. A protostar formed. A star ignited, burned through its fuel, and at the end of its life, scattered those atoms back into the interstellar medium, where they drifted, cooled, and eventually became part of a new cloud, a new collapse, a new star, our star. And from the disk around that star, those atoms became part of a planet. And on that planet, they became part of you. That is the heritage. Now here is what we still do not understand. The process described in this story is real and well supported, but it is not complete. At every stage, from the first fragmentation of the cloud to the ignition of hydrogen in the core, there are questions that remain genuinely unanswered. Not because the science has been neglected, but because the answers are extraordinarily difficult to obtain. The first and perhaps most fundamental mystery is the initial mass function, the statistical distribution of stellar masses produced by a collapsing molecular cloud. Every star-forming region in the galaxy produces roughly the same pattern: many low-mass stars, fewer intermediate mass stars, very few high-mass stars. The shape of this distribution is remarkably consistent across wildly different environments, different clouds, different galaxies, different epochs of cosmic history. And no one fully understands why. Something about the fragmentation process, the turbulence, the interplay of gravity and pressure produces this specific distribution with striking regularity. But the mechanism that sets it, the reason the universe makes so many small stars and so few large ones, remains an open problem. Magnetic fields, despite decades of study, remain contentious. Observations have confirmed that they are present in every molecular cloud, threaded through the gas at strengths that should in principle matter. But how much they matter, whether they are a primary support mechanism that fundamentally slows star formation, or a secondary player that adjusts the details without changing the outcome, is still debated. Different groups, using different methods, reach different conclusions. The observational constraints are improving, particularly with sub-millimetre polarimetry from facilities like ALMA, but the question is not yet settled. Then there is the problem of massive stars. Everything described in this story applies most cleanly to low-mass stars, objects like the Sun, and smaller. The physics of collapse, accretion, and contraction is well understood for these objects. But stars 10, 20, 50 times the mass of the Sun present a puzzle. They are so luminous, even during formation, that their own radiation should push away the infalling gas and halt accretion long before they reach their observed masses. How they continue to grow, whether through disk accretion shielded by the geometry of the infall, through competitive accretion in dense cluster environments, or through the merging of smaller protostars, is a question that different theoretical models answer in different ways. None has yet achieved consensus. The efficiency problem remains stubborn. Only a few % of the gas in a typical molecular cloud ever becomes stars. The rest is dispersed, blown away by feedback from massive stars, stirred by turbulence, heated by radiation, and returned to the interstellar medium unused. Why the efficiency is so low, and what determines its precise value, is not fully explained by any single model. Turbulence, magnetic fields, and feedback all contribute, but their relative importance varies from cloud to cloud and from simulation to simulation. The answer is probably not a single mechanism, but a conspiracy of several, and disentangling their contributions remains an active frontier. Perhaps the most exciting open question lies at the intersection of star formation and planet formation. It was once assumed that these were sequential processes. First the star forms, then the disk settles, then planets begin to coalesce. But observations from the James Webb Space Telescope and from ALMA have challenged that picture. Dust grains in protostellar disks appear to be growing, clumping together, building the first solid structures, far earlier than previously thought. Disk chemistry is complex and active even during the embedded protostellar phase. The raw materials for planets may be assembling while the star itself is still accreting, still contracting, still millions of years from the main sequence. If this is confirmed, it would mean that the story of planetary formation does not begin after the star is built. It begins during the construction. The two processes are not sequential. They are simultaneous. And beyond the physics of individual stars lies the largest question of all. Star formation does not happen in a vacuum. It happens inside galaxies. Structures that are themselves evolving, merging, interacting, and changing over billions of years. The rate at which stars form in a galaxy determines its brightness, its colour, its chemical enrichment, and its future. The deaths of massive stars, the supernovae that trigger new collapses, return heavy elements to the interstellar medium, enriching the next generation of clouds and the next generation of stars. Star formation is not just a local process, it is the engine that drives galactic evolution. Understanding how the small-scale physics of collapsing cores connects to the large-scale evolution of entire galaxies is one of the grandest challenges in modern astrophysics. The bridge between the two, between a single core and an entire galaxy, is not yet fully built. Every answer in this story has opened a deeper question. Every mechanism that has been identified has revealed a layer beneath it that is not yet fully understood. And that is not a failure of science. That is the nature of it. The process of star formation is one of the most studied phenomena in astrophysics, and it remains one of the most active fields of research precisely because the more we learn, the more we realise how much remains to be found. So return, now, to the question that started this journey. How does empty space build a star? The answer is deceptively simple. A few atoms of hydrogen, drifting in the cold dark between the stars, are gathered by gravity. They accumulate, they form a cloud. The cloud cools, condenses, and fragments. A dense core crosses a threshold, and gravity overwhelms the forces that held it apart. The core collapses. It heats. It forms a disk, launches jets, and accretes mass from its surroundings. It contracts for millions of years, descending a path first mapped by a physicist in Kyoto, glowing faintly in the infrared, invisible to the naked eye. Its core temperature climbs, past 1 million Kelvin, past 5 million, past 10. And then, in a moment no external observer would notice, hydrogen begins to fuse into helium. Pressure meets gravity. The contraction stops. A star is born. That is the answer. But the weight of it lies not in the summary, but in the details. In the 100,000 years of invisible free fall. In the two-stage collapse that Richard Larson computed on machines less powerful than the phone in your pocket. In the magnetic fields that resist and yield. In the jets that scream outward at hundreds of kilometers per second from objects smaller than our solar system. In the disk that feeds the star and builds its planets simultaneously. In the cluster of siblings that will scatter across the galaxy and never find each other again. In the 4 million tons of matter converted into pure energy every second of every day for billions of years. inside an object that started as nothing more than a few cold atoms in the dark. You are made of this process. The iron in your blood was forged in a stellar core that formed this way. The oxygen you are breathing was scattered into space by a star that died so that the cloud which built our sun could be enriched with the elements necessary for rocky planets and liquid water and everything that followed. You are not separate from this story. You are a consequence of it. A late chapter in a narrative that began with nothing but hydrogen and gravity and time. And tonight, somewhere in this galaxy, in a cloud you will never see, in a darkness you will never touch, it is happening again. A few molecules are drifting together. A core is forming. Gravity is tightening its grip. And in 1,000,000 years, there will be light.